Heyo everyone, you're here because you want to see a redstone maze generating in 1 second, so without any further preamble, there you go. For those of you just joining us, this is part 3 of a 3-part series on maze generators in Minecraft. In part 1, I ranked a bunch of existing maze generation algorithms on how well suited they were for redstone. In part 2, I went over how I developed a new algorithm that this maze generator uses, and here in part 3, I'll be demoing the redstone of this maze generator. If you want a more complete overview of the algorithm, check out the second episode of this series, but just as a brief recap, we essentially take the Hilbert curve and overlay that on our maze, and then for each cell in the maze, we choose a random neighbor that's further along the Hilbert curve than we are, and we remove the wall between us and that cell. Each cell only needs to know which neighbors are valid targets, and other than that, each cell can work completely independently. A few notes before I get into the main explanation. This build does rely on the experimental redstone features that have been in the recent snapshots. It's possible to make one that's almost as fast without them, but they allow me to save just a few extra ticks to get the generation down to 1 second per generation. You'll also see there are a few command blocks here. These ones here are just for teleporting around the map to get to different viewpoints. And these ones are not actually connected to the maze generator. These modify the maze generator in a few different ways so that I can switch it between this algorithm and the binary tree algorithm and a few others quickly, because the underlying mechanism is the same. It just needs a few tweaks to each cell to get different types of mazes. So I'll show that off at the end of the video. But for now, let's take a look at the redstone. Here we have a single cell of the maze in isolation. Because each cell operates independently, there's not much more to explain beyond just how a single cell works. Each cell is 7 blocks by 7 blocks, but 1 block in each wall is shared with the neighbor. So for scaling, they're effectively 6 blocks by 6 blocks, plus 1 extra row and column at the border. If we come down here, we have our main inputs to the cell, are these 2 instant repeater lines. This is what allows each cell to start generating on the same tick, and these feed into this latch system. So when the reset line goes high, we get our latch system set where this torch is powered and this one's depowered. And when this one goes high, we go in the other direction where this torch is depowered and this torch is powered. You'll note here there's also a diode going from the generate line into the reset line. This makes sure that we trigger a reset before each generation. I'm going to freeze the game real quick, just so I can step through this 1 tick at a time, just to show that it does generate in exactly 20 ticks. Now the game is frozen. I'm going to press this button. You can see we have the redstone goes high, but nothing actually triggers yet. I'm going to be stepping through 2 ticks at a time, which is 1 redstone tick. Even though redstone ticks are fake and made up and don't actually exist in Java, that's the term everyone uses, so that's what I'll be using. So, the first few are rather boring. We trigger this reset line. The system was already reset, so nothing happens. Do 3 more. Now things get interesting as we start triggering the generate line. So this has been triggered, this torch will soon turn off, and when that turns off, this redstone will also be turned off. And one of the experimental redstone features that this relies on is that when multiple redstone components are powered or depowered on the same tick from the same signal strength, there's some randomization on which one gets to go first. So when this gets depowered, it will randomly choose one of these pistons to retract first and pull this composter with it. Alright, so it randomly chose this one. Now this comparator will turn on next, and that will trigger this chain that will open up this piston door and turn on these lamps. So let's just step through a few more. We got this redstone torch line going. We got both of those triggering at the same time for a smooth open. And then those lights turn on. At this point, the entire maze is generated. All the doors will be open. All these lights will be on. And if we look at chat, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 2-tick increments, which is exactly 20 ticks. And at normal game speed, that would be exactly 1 second from the tick the input is triggered to the maze being generated. I'm going to unfreeze things real quick. And like I mentioned earlier, this diode line allows it to be reset and generated at the same time. So I'm going to freeze the game again, just to show that this works in a single second, even if it's already been generated. I'm going to step forward 20 ticks. And there we go. We got a new generation within a second from a previous one already existing. And believe it or not, that part was actually the hardest to get whittled down. I mean, there's 6 extra ticks here. I got everything building in 14 ticks, and it took like probably 3 weeks of tweaking just to get this input system set up so I could have it generate in 1 second from already being generated instead of just from blank. Yeah, that was a pain. But yeah, that is it for the redstone. I guess the only other part is down here with these command blocks. The command blocks here are what allow each cell to know which neighbors are valid targets. You may have noticed that up here we have pistons in all 4 directions, which would lead to a mess that wouldn't actually most likely be a maze if every cell could open into any of its neighbors. So that's where this layer comes in. These command blocks will be triggered in a different sequence depending on which maze you're trying to generate. When it's triggered, it checks the 4 neighbors to see if there's still green wool above them. If there is, it leaves the piston alone. Otherwise, it replaces it with just red concrete to mark it as invalid. And then after all those checks are done, we replace this green wool with red wool so that our neighbors know we are no longer a valid target. And then over here, I have just this little system with 4 different configurations that I can load into the system. Let me just make sure everything's cleared here. And I can copy, let's take a look at the binary tree. Here I just have repeaters going in these 2 directions. So we start in this corner and end in this corner. Those all got copied over here, which then swapped out some of our pistons with this red concrete. And if I go to generate, we have our very distinctive zigzag pattern going from that corner into this corner. Just to show off the other couple of ones I have, this yellow, or this pink line here, is the midpoint tree. This is the one that is basically 4 smaller binary trees all hooked up together, pointing towards the center. Like I mentioned in the previous video, it's a bit of an improvement, at least visually, but is still very straightforward to solve. The next one that I have set up here is the spiral lookahead. This is just a giant spiral. If you look here, I have this little chat command set up to just run the tick sprint, just to allow it to get to all of the cells faster. Otherwise we're waiting 1 repeater for the entire 16 by 16 grid of cells. And I'll just generate this one. Here you can see there's still, distinctly these large regions where we're kind of going diagonal in the same direction, but especially on the main diagonals and near the center, there's a lot more randomness. There's things that are potentially more confusing. And then, of course, the final setup I have is the Hilbert curve. So I'll just copy that to generator and the workspace. Accelerate it again. Yeah, here we have a giant 16 by 16 Hilbert curve. And just like at the start of the video, we can generate a maze in in exactly 1 second. And then just to show off that we can generate even when there's already a maze there. There we go. But yeah, that is it for this redstone build. Thank you for watching. A big shout out to Captain Luma for inspiring me to make my own redstone generator. And another shout out to Rapscallion, who helped me with some of the redstone. I didn't end up using any of his designs, but he had a really good design for the randomizer bit here that doesn't rely on experimental features. And if you check out his channel, you can find a video of him making a Prim's algorithm generator using that randomizer. But yeah, other than that, thank you for watching, and I hope you enjoyed this episode. If it's something you enjoyed, consider leaving a like or subscribing, and I hope to see you all in the future.